Terry Engelder is actually a native of Central New York, and we also share something in common. We both have a Bachelor's of Science from Penn State, so that's kind of cool. He went on to get his master's at Yale and then a PhD at Texas A&M. And he's had a very diverse career in just about all the different places that one can work as a geologist, almost. He's been employed by the U.S. Geological Survey, by Columbia University's Lamont Doherty Earth Observatory, and of course by Penn State. And he has also spent some time as a geologist for Texaco. His interest in the Marcellus Shale gas play is partly an evolution of his expertise in a long career in the evolution and tectonics of the Appalachian Basin. And of course those black shales are an important part, and their joint structures are an important part and piece in our unraveling the geologic history of the Appalachians. And so his evolution toward interest in the Marcellus Shale play comes naturally out of his research career. In addition to having a lot of conversations like this with a diverse audience on the Marcellus gas shale play, he's also the only scientist on the Pennsylvania Governor's Marcellus Shale Advisory Committee. So the rest of that committee is made up of folks who don't necessarily have that scientific expertise, so he brings that to that conversation as well. So we have about probably 40 to 45 minutes of talk, which will introduce you to the Marcellus Shale and its exploitation, and then we hope to open it up to about an equal amount of time for conversation and questions. So I hope you all brought your questions and your curiosity and your concerns, and we hope that you will have an opportunity to share those this evening. So without further ado.
Okay, thank you, Nan. What a pleasure to be here. When I grew up, on occasion, my parents would drive me up to watch Syracuse football, and the route that we took from my hometown, Wellsville, which is on the Genesee River, to Syracuse, was right up Route 14 here. And so you can assume that as early as about 1960 or something like that, I started driving along this road right here and past the William Smith campus, although I've never given a formal talk here, so it's my pleasure to be here. First of all, let's talk a little bit about scholastic excellence, because that really is what this is about. You're here as scholars to try to understand fracking and the details of it, and with the information you're going to get from talks like this, you're going to make a decision one way or the other as to whether fracking is a good idea or not. And so in a sense, what you're trying to do is achieve a certain degree of scientific excellence. Now let me point out that it's been my pleasure over the last 35 years as faculty member, first at Columbia University, then at Penn State, to have former students, Nan, of course, being one of those. And I have to say that Nan, as a student, was just unbelievably good. And she would be just a great model in terms of how I would hope your careers turn out. Nan is a mom and a scholar, and hopefully just generally, and I know this is true, an asset to the university. And one of the things that Nan exhibited when she was a student was a combination of curiosity, passion, and total engagement. And that's what I would hope that all of you strive to become too, is someone who represents scholastic excellence through a combination of curiosity, passion, and total engagement. All right, now, what is my role? Or for that matter now, what is Nan's role as a teacher? Now, this is probably one of the most famous of the early 20th century poets, obviously Arabic, Khalil Gibran, and his view of a teacher is expressed here in Arabic. I've translated for you. If he, the teacher, is indeed wise, he does not bid you, notice it should be he or she, does not bid you enter the house of his or her mind. That's very important. The teacher is not here to proselytize. Now, one of the misleading parts of the announcement today was that it was announced that I'm an advocate of gas shale. No, that's not entirely true. I'm really here to give you the facts and allow you to decide for yourself about gas shales. So what really the mission of a teacher, my purpose here, is to lead you, the students, to the threshold of your own mind. And this becomes a very, very important distinction between those people who are advocates and those people who really are trying to tell you one thing or another about the science. Okay, now, one of the things that it has been my distinct pleasure in terms of the fracking debate is that I've been central to this for the last half decade. And it has been one of the more exciting scientific debates that we've had in America and, in fact, globally. Because, of course, I've been to a number of countries that have decided to ban fracking, including South Africa. I was invited by the French national oil company Total to try to settle that population down, and they wanted me to speak to a reporter from Le Monde, and I noted in the student center here, newspaper, no, it was the library where I saw that, a copy of Le Monde. And unfortunately, the legislature voted a ban on fracking, or at least a moratorium on fracking, before Total could get me to the reporters. All right, so what is this debate all about anyway? And what I'm going to do is explain that there are analogs to the fracking debate, and one of the best analogs concerns two books that have been written about the collapse of societies. And one was written in 1988 by Taylor, and his thesis was that it was basically the lack of energy capture that led to a law of diminishing returns and therefore a collapse of the society. On the other hand, Jared Diamond's famous book, written a number of years later, argued that it was environmental mismanagement. So here we have two very good books. I recommend that you read both of them with two completely different theses. One was driven by environmental issues, and the other was driven by energy issues. And this really is just exactly what the fracking debate is about. Nan passed around a PDF file and recommended you take a look at this Nature article that was written a year or so ago with the question, should fracking stop? And this was a point-counterpoint. And I wrote about the counterpoint, no, it's too valuable. So this is the economic side of things. The point was defended by my Cornell colleagues, and yes, the fracking should stop. It's too high risk. And so here we have again this same type of debate. Tony Ingraffia, who incidentally I've written a paper with, in fact, is with this Science or Nature paper now too. And Tony has taken the side of the environment, and I've taken the side of economics. And it's been a lot of fun. Tony and I have gotten together just recently. We were both at the annual meeting of the Society of Environmental Journalists. And the president of the society pointed out during our meeting, this was just actually a couple of weeks ago down in Lubbock, Texas, where the president of the society pointed out the environmental issues have taken a back seat to the economy and job creation. And you did not hear much about the environment in the presidential debate or the vice presidential debate. But environmental issues continue to be important, especially climate change, and of course there's the word fracking right here. So the fracking and environmental climate change then emerge as the two singular most important issues to be debated, both in the public and then in public forum policy. So it becomes a very political debate. Goes beyond science. Now, one of the things that I should point out, however, is that from the scientific point of view, there's no right answer and there's no wrong answer to scientific debate. But there is an extraordinarily large amount of propaganda. Now, this becomes very interesting because I think that a lot of you know that Josh Fox's movie is extraordinary in the extent to which it is based on innuendo, not scientific fact. And interestingly enough, another movie was made. This was a gas industry pushback called Truthland. I don't know that any of you have seen that. Truthland also, I have to say, contains a little bit of innuendo. And I won't tell you about it, but rather if you wish to watch that particular movie, and if you've done that and been unable to identify the innuendo in Truthland, email me and I'll tell you what it is. At any rate, what this says right in here is that a filmmaker asked Josh Fox about lighting water, and Josh Fox's movie, by innuendo, implies that lighting faucets had something to do with fracking. And this particular documentary filmmaker asks Fox, you said yourself people lit water long before fracking started, isn't that correct? Fox's answer, of course, is yes, I knew that, but that didn't serve my purpose. This is the type of propaganda that's out there. This is the type of propaganda that we would hope the student would be able to recognize and understand. In other words, you can't really rely on what you've been told without going out, without reading the books, without reading Jared Diamond's book, without reading Tainter's book. Now let me go back here and point out that a notebook is being passed around the room. It's this notebook right here, which 2 weeks ago was passed around in the Czech Republic. In fact, as if you leaf through the book, you'll find people that have signed that. That book is now going up the far side, and the gentleman in the back corner has it. If you could pass that over, once you've signed it, your name, your major, and your hometown. And this is a notebook that I pass around for every talk I've given. So, at any rate, here's the situation, which is that why is it that environmental issues have receded? I think the answer is really quite simple, which is that often in human experience, time scale matters. And in fact, it's the short-term time scale or the short-term needs that trump long-term needs. And so I've identified the short-term needs, usually political, short-term time scale, intermediate time scale, socioeconomic, and long-term time scale, environmental. We all recognize that climate change is a very, very serious issue, so you might ask, why is it that I chose in this debate in nature to take the side opposite from that Tony Ingraffi of Cornell decided to take? And the answer really is quite simple, which is that I think that socioeconomic collapse and chaos has a much shorter fuse on it than the environmental issues, particularly in terms of climate change. And furthermore, it is very clear that a society in economic chaos can do very little about affecting climate change, whereas a society that is a very robust and economically healthy society is a society that can then step forward and actually do something about climate change. If you're the Chinese government, then I hate to admit it, but I don't want us to end up governed the way the Chinese do. And yet there are advantages to that political system, and one of them is that they can cross off the really short-term political time scale and make some decisions about an intermediate time scale and possibly even a long-term time scale, whereas we tend to be quite politically hamstrung. Polarized, if you like. So, at any rate, risk. I told you that I talked to you about risk, and a cost-benefit analysis is the same thing as a risk-benefit analysis. Cost here equals risk. There are two issues, one of which is government and private businesses evaluate this cost-benefit or risk-benefit to evaluate the desirability of a given policy. Now, in this case, for example, the government is looking very carefully at fracking and trying to understand the risk and trying to understand the desirability then of a certain way of managing this risk. The Environmental Protection Agency is charged with that. Now, cost-benefit analysis can offer a well-educated estimate of the best alternative. But I should point out, and it's important to emphasize, that perfection in terms of economic efficiency and social welfare are not guaranteed. Now, this is a statement that an economist might make. An equivalent statement that a scientist might make, and I want to make this very clear also, is that there is no absolute truth in science. And in fact, science is designed to identify those things that are not true and scratch them off the checklist, leaving other things that need examining. And eventually, through years and years and years, scientists iterate towards the truth. They never arrive at the complete truth. And in fact, this is where your education comes in. You are going to be in a situation where you will seek the truth. You may never arrive at the Holy Grail. All right, now risk. 3 types of risk that I want to talk about. One of which is that there are, anytime there's a risk, there's also a benefit as well. So financial risk, examples of financial risk, government-funded research. You will have to say that the Obama administration took a great deal of heat for funding a company to try to build at an inexpensive price solar cells, and that company went bankrupt. So the government took a risk. The benefit was that America was going to manufacture internally cheap solar cells. The risk was that the Chinese would do them one better, and that's what happened. An IRA, anyone that's my age knows the extent to which my retirement depends on the performance of the stock market. There's a risk and a benefit. Real estate investment, you all know about the collapse of the 2008 banking. Investing in gold, you've seen a lot of ads on TV recently. Invest in gold, that's the best way to save money and whatnot. Poker is another example. All right, environmental risk. Each source of energy comes with a risk, and you should be well aware of this, that there is no renewable energy that doesn't have a risk. There is no hydrocarbon energy that doesn't have a risk. And all I've done right here is just list the 6 major sources of energy for America: wind, solar, hydroelectric, coal, oil, gas. All of them have their own risks. None of them are risk-free. And what we're going to do is of course, talk about gas and the risks associated with fracking. How about physical risk? Again, there's possible harm associated with the activity. The activity here is driving cars in America. And I draw your attention to the number of deaths, highway deaths per year in America in 71, 72, and 73, 52,000. Now, for anyone in the audience that is as old as I am, you'll recognize that those numbers are comparable to the number of deaths during the total Vietnam War. The per annual death rate killed in action was on the order of 3,000. So here actually is an incredible risk. And one of the things I have to say is I've spent a lot of time in and around the fracking industry, and I can assure you that statistically, I took a far larger risk getting in my car this morning, driving up here to give this talk, than I ever have dealing with the fracking industry and each of the processes. Now, one of the important things about this table, you see 2008, 2009, 2010. Notice the highway deaths are significantly lower 30 to 40 years later. Particularly, risk is measured by the number of highway miles driven, for example. And look at this. What has happened is that the number of fatalities per highway mile driven is 1/4 now from the rate that it was when your parents were around and your grandparents were driving. And the lesson right here, and this is an incredibly important lesson, is that risk can be mitigated over time. Now I put that up and emphasize that because yes, there have been such things as spills associated with fracking, but as industry goes along, it's going to get better and better and better. And in fact, I would submit to you that this fatality rate demonstrated here over a period of time is a great model for what's going to happen with industry as industry moves along with time, particularly with the encouragement of the EPA. It's going to get better and better and better, but this is an industry like any industry where there will always be risks. And you might ask, how many people were killed in Pennsylvania last year as the result of fracking? And the answer is 2. Whereas there were several thousand highway deaths last year. You would conclude from that that driving an automobile is a far riskier business. But society has, as a body, accepted that risk largely because it recognizes the tremendous convenience involved in driving a car. And so the benefits then in the mind of societies outweighs the risks to the point that we all get in a car, and as we drive towards one another on a road, we're willing to accept the risk that the person coming towards us is not going to immediately plow into us. All right, now a little bit of a conversation about energy is in order here. Let me just remind you the units of energy include energy power. Energy is kilowatt hour. Remind you that kilowatt hour is measured in British thermal units, 3,400 British thermal units, or 36 million joules is equivalent to a kilowatt hour. On the other hand, power is the use of energy per unit time. And of course, you all recognize that driving a car gets you places faster than riding a horse. Why? Because the motor of a car is many, many horsepower. Here's megawatts. And the reason I use the word megawatt here is we think of wind energy in the general turbine. Wind turbine is on the order of a 2 megawatt turbine. And I made a mistake right here. You need to multiply that by 2 to find out how many horses is equivalent to the energy generated by a 2 megawatt wind turbine. All right, now, how has energy affected society over the last 60 years? And here's where I suggest that you take a look at the literature again. A number of books, Huber and Mills pointed this out. And this diagram right in here comes from Bryce's Gusher of Lies, the dangerous delusions of energy independence. There are a number of these things that you really want to read before you make a judgment about whether or not fracking has merit to it. I mean, you just cannot listen to one movie or your friends and make a decision one way or the other. It takes a great deal of study and a great deal of effort understanding economics, politics, science, and a number of other academic subjects. But at any rate, the point of this particular diagram is that from 1950 to the present, the total American energy consumption in quads was on the order of 100 quads of energy. And just to remind you, going backwards right here, 1 quad of energy is equivalent to 10 to the 15th BTUs. That's quadrillion BTUs. Or if you like, 292 billion kilowatt hours. That's the total energy usage in the U.S. Actually, you multiply this times 100 to get the number of kilowatt hours that are used. So it's up in the trillions. So at the same time, we see that the energy cost of the economy in thousands of BTUs per GDP. And look at this spectacular decrease. And what that really means is that there's a direct correlation between our lifestyle and energy. But more importantly, our lifestyle is far better than our parents, much better than our grandparents. And that's simply because in America, we've learned how to use energy much more efficiently, and by this efficient use of energy, we've actually improved in the way that we live. Energy and lifestyle correlate with one another, and this is incredibly important to appreciate and understand. Basically, the energy benefit here is a higher living standard now than when your grandparents were alive. There's another diagram that is important. This is Huber and Mills' book, The Bottomless Well, which I invite you to read. And what Huber and Mills point out, and this actually is done through the CIA, among other things, is that the GDP for the economies can be measured in the amount of money that's in circulation. And it turns out that the number of BTUs used per capita correlates with GDP. And of course, as I've already indicated, GDP is lifestyle right in here. You enjoy the lifestyle that you enjoy largely because of energy. Very important thing to keep in mind. So this again is the energy benefit. And I put over here just to remind you, this axis right here is in fact lifestyle. The people in Indonesia, China, Brazil, Iran have a much much more difficult lifestyle. Difficult in the sense that they don't have the conveniences that you have, the conveniences that you know are brought to you purely by the expenditure of energy. Energy density is another concept. And here's a very famous Canadian ecologist and economist who points out that energy density is basically the amount of energy that you can get out per unit weight of any type of energy. Wood, for example, I want to compare wood and natural gas in particular. This is a log scale on the vertical axis, and just right now you can see that per unit weight, natural gas ends up giving you 10 times the amount of energy as an equivalent weight for a wood. Now, in terms of energy, nuclear energy is the king right here. And in my view, it was really tragic when the environmentalists of the 1970s shouted down the nuclear industry and shut it down largely because they viewed it as somehow or another harmful to the environment. And now, 35 years later, I guarantee you there are a whole bunch of environmentalists that are saying, my God, look at what happened. We have global climate change as the result of CO2 emission from coal-fired power plants because we shut down the nuclear industry, which basically has zero emissions in terms of CO2 and the global warming gases. Look at what we did. Okay, so it's interesting that I was in a debate with the mayor of Binghamton, and any of you that are from Binghamton are aware that the mayor has been very outspoken about not allowing natural gas production anywhere near his hometown. And in fact, is when asked, well, how are you going to heat your house? He's perfectly content to have his people in Binghamton burn wood chips for residential heat. And he has said this over and over again publicly. Let me just remind you that the energy density is such that 10 times the weight of wood is going to have to be burned to keep people warm relative to natural gas. So that one has to start thinking about these things when there are the various energies and the various solutions proposed for such things as residential heating. Power density. Power density right here is defined as the area necessary to generate a certain amount of power. Nuclear power plant, a 2,700 megawatt nuclear power plant will occupy this area right in here. Wind energy, however, to generate the equivalent wind energy and electrical energy is going to require a huge area relative to a nuclear power plant. So one of the other considerations is use of surface area. It really becomes very important to think about these things. And incidentally, the wood chip guy down in Binghamton, can you imagine the number of trees that he's going to have to grow each year to chop down to keep the houses in Binghamton heated? And I guarantee it's an area larger than Broome County. He's liable to have to come up here to Ontario County to have some of his wood grown. All right, let's actually look at wind power. This is another very interesting diagram right here. What I've done is I've indicated here that unless the wind is blowing at a speed that will generate about 400 watts per square meter, basically the large wind turbine is the target, and every square meter of that target has to generate 400 watts. If it's any less than that, then it really is not sufficient for economic or even efficient wind capture. And so the area that's capable of generating sufficient electricity so that we can capture, let's say this 100 quads per year. This is the U.S. energy consumption right here. So what is the area covered by 2 megawatt wind turbines that is sufficient to allow America to generate the energy that it needs for the lifestyle that you know today? And if you look at this color right in here, let me point out that the plains, this area right in here, there's 2 or 3 spots there, and there in New York State. Those are the only spots in New York State that have sufficient wind, on average 400 watts per square meter to generate power. in order to generate the equivalent of 3,300 gigawatts of power, which is what this energy consumption is in America, basically you would have to have a 2 megawatt wind turbines per square mile, and the distribution of those wind turbines would be over this entire area that I've just outlined right here. So that what that means is that if you were to drive from the Canadian border down to Mexico, along the Great Plains right here, anytime you stop the car, mile after mile after mile, you would be able to count about 20 wind turbines within your line of sight. Every mile, mile after mile after mile. That's how many would be required. And that doesn't indicate how the wind-generated electricity is going to be carried from Oklahoma to New York City. That's another issue that we'll save for another day. Okay, even looking at New York State. New York State right now has an installed capacity of 1,400 megawatts. New York State consumes at peak demand 34,000 megawatts. And in fact is, going back to this rule of thumb, that 400 watts per square meter is what's required to generate electricity. The maximum potential that New York State has is only 7,000 megawatts, or in other words, about 20% of all the energy that New York State generates. So that moving forward, then, New York State has to come up with some other plan to generate 80% of its electrical power. It cannot rely on wind as a renewable. All right, there's another thing that enters into this capacity factor, which is that capacity factor is defined as the ratio of reliable power to total generating capacity. Basically, we don't want brownouts. You want these lights to stay on 24/7. And that means the electricity has to be generated 24/7. And if you have a wind farm of, let's say, several hundred turbines, portfolio across New York State, 24/7, 365 days of the year, only 7% of that wind farm capacity will give you reliable electricity. Now what that really means is that despite the fact that you may have a potential down here, New York State may have a potential of 7,000 megawatts. That 7,000 megawatts has to be backed up by some other source of power that can be turned on and off. 93% of that has to be backed up. And you know what the proposal for backing that up is? It's combined cycle natural gas turbines, fracked gas. There is no other solution right now to this particular type of renewable green energy than to back this up, unless you want brownouts. I mean, I'd be glad to have these lights turn off for several hours a day in parts of the year, but these are the realities. So there's a trade-off right here, and you've got to go into that. Talk about fracking gas, the fuel that keeps Geneva homes warm right in here. Let me point out that natural gas is used to heat 85% of all homes in Geneva, and it's all fracked gas. So one benefit from a practice that some consider as risky, anyone that heats their homes, not anyone, but 85% of the people that heat their homes in Geneva are heating their homes with fracked gas. It's a fact. All right, so how does that fracked gas get to Geneva? You can get on a website and look at the pipelines right here. Here's the flow of Marcellus gas to New York State, and largely it's the Dominion pipeline actually that serves Geneva right here. And the core of Dominion capture for gas is fracked Pennsylvania right here. So these are the realities. So the public is concerned in Pennsylvania that Marcellus frack fluid can mix with groundwater, thereby causing an outbreak of health-related problems among those who drink well water. All right, this is a concern that's very real. It's expressed by a fractivist known as Wendy Lee right here. She has a website called Raging Chicken Press. She writes the toxicity of chemicals involved in the fracking process itself and the veritable certainty that these will leak along fissures into well casings in the groundwater. This is the issue right here, and the question, of course, is this word right here. This should frighten the living daylights out of anyone, that there is dead certainty that any well that's fracked is going to poison groundwater. Basically, that's what she said. And I'm a geologist, and I'm going to spend the next 30 minutes, not 30 minutes, next set of time with you talking about this particular issue right here, whether this is true or not. And first of all, let me indicate that EPA, I can assure you that EPA is really looking into this to study the problem. And the problem basically is one that revolves around the injection of water in the fracking process. Now this is a diagram. I'm assuming that everyone in the audience has seen this diagram. The Marcellus Shale in Pennsylvania is down around 7,000 feet. Here's the groundwater right up in here like this. Now, what I've written right here is that there are engineering solutions to a number of these problems. The only one that is really outside the realm of engineering is what controls the fluid that's pumped down into the ground right in here like this. Just as an aside, let me say that I've given a number of talks a number of times where someone has stood up and said, well, what about the water that's used for fracking that's removed from the hydrosphere? Isn't that ruinous, et cetera, et cetera, et cetera? And the answer to that is very quickly expressed by saying that the amount of natural gas that's burned relative to the amount of fluid that's used, water that's used for fracking, more than replaces water in the hydrologic cycle by this particular reaction right here. When you burn natural gas, it's natural gas plus water plus oxygen equals CO2 plus water. So what we're going to do is focus on this question right here. Some people have asked, well, the Marcellus, this is a picture of the gas shales filled with cracks right here. Don't those cracks allow these injected fluids to the surface? And the answer is simply this. This is a diagram right here that expresses the Marcellus at depth. This is in meters. Right in here, there's another gas shale right here. The Marcellus is the region in which these particular fractures form, and those fractures are not continuous to the surface. Notice the shale rocks in between do not have those fractures. And so, in effect, what happens then is expressed by the award-winning geophysicist named M. King Hobart, who points out that despite the presence of fractures in rock, here's a red rock right in here, the fractures here, 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 and here. What he says in this diagram basically is the permeability is not the permeability of fractures, but rather the rock. The rock is capable of keeping that fluid in place. Aside from which, that frac fluid at 7,000 feet does not flow uphill. I mean, this is a fact. You cannot dispute the fact that water flows downhill with gravity, not uphill against gravity. All right, now let's talk a little bit about economics of gas shale production, which is, have you guys signed that book instantly over there? I see you passing it on. You've all done it. How about the middle section then, over here? Has that been through the middle section? I see a thumbs up. Okay. Right through here, this is a diagram of the volume of production of two gas well fluids. One of them is the water that's put down in the well, and that flows back in a very short period of time early after the hydraulic fracture stimulation. And the other is the production of gas. The production of gas is shown in red. The production of fluid put down is shown in blue. All right, let me make it clear that gas well production is really dependent on having this fracking fluid, which is what Wendy Lee speaks about as being an issue. As long as that fracking fluid sits in the fractures that are made in the rock, and I've shown you a bunch of those fractures just by going back here. As long as the frac fluid sits in those fractures, gas can't flow out of the well. That's the first thing that has to happen. Now that's why you see flowback, because gas under pressure pushes the water out of these cracks right in here. The fact is that fluid largely is designed to carry sand down in the well, and the sand will prop these cracks open so they can flow at a reasonable rate. And so basically what happens is this gas right here, the early production of gas, pushes the water called flowback out of the way of the well. And as that water is pushed out of the well, then gas production can increase a great deal. There's always a little bit of fluid that returns to the surface, but not a lot. This fluid I've distinguished from the early water coming back. Flowback water comes back before peak of gas production, and production water after peak of gas production. Now the interesting thing is that the fluid that's put down into the ground, total amount of fluid put down in the ground, we call this treatment fluid. Of that, the amount of fluid that comes back out of the wellbore, what this table says is a complex table, but the only thing that really is significant in this table is that the average amount of injected fluid that comes back is 11%. On average, 89% of the injected fluid is still on the ground now, and on average over a long period of time, industry is shown that 80% of the water stays in place. So in the public's mind then, the question is what happens to this 80%? Because that's the water that everyone is concerned about getting into groundwater. And what happens to that? And there's a very easy way of talking about that I hope I can help you understand. There's an interaction between a fluid and a solid right here. All of you have seen the fender of your car after you've waxed it. After the fender of the car is waxed, water on that fender will bubble up. If the fender is dirty, on the other hand, water will smear across the surface in a flattened way. And this indicates that the surface of your fender can be wettable. And basically what happens is, as you drive and it rains, dirt gets on the car, and it's the dirt that turns the fender from a non-wettable surface to a wettable surface right in here where the water can spread out. Now, does everyone know what I'm talking about right here? Because the points that I'm going to make in about the next 10 minutes are all going to revolve around you having observed your car fender, having owned a car or polished your parents' car, and seeing the difference between the beads of water after you wax the car, and then when the car gets dirty, how the water smears out. In one case, we say the car fender is water wet. In the other case, with the wax on the car, we say the fender is oil wet. Okay? So, in an oil reservoir, it turns out most oil reservoirs are water wet, which means that the grains themselves, the sand grains, for example, in a reservoir have a film of water around the surface of them, and then oil sits in the pore space right in here like this. So this is another concept that allows us to jump from the car fender to real rocks. Most of the gasoline that you burn was driven out of rocks that are acting like your car fender when your car fender is all dirty. In fact, that's the property of the rock that allows for oil production. If the rock did not have that property, oil could not be produced. All right, now, the next concept. I come from Western New York, where they have and grow the world's best water skippers. I'm sure all of you have seen these guys on ponds right here. And you've seen the water skipper on the pond depress water around each of its 6 legs. This is an insect where the bottom part of the leg actually does not sink through the water, but depresses it. That property of the water that allows the water skipper to support itself is known as surface tension. And surface tension can be expressed here by the fact that surface atoms are attracted to one another with enough of a force that it's difficult to pull them apart. So it's that surface tension between molecules of water then that allow the water to hold together as the legs of this water skipper are depressed. Surface tension. So we have 2 concepts now, wettability and surface tension, and they both play a role in what happens to that frac fluid. Now we can do a scientific experiment that I'm sure that many of you have done. Many of you have taken a glass straw or even a paper straw at McDonald's and observed water in the paper straw. And I'm sure that all of you have seen that water is drawn up the paper straw or the glass straw. You can do this in a physics experiment. And when water gets drawn up a glass straw, it's drawn up because the edge of that water, the contact between the glass straw and the water, is water wet. You also have observed this cone of depression right in here. That's a consequence of surface tension. Anytime you bend the surface of water against gravity, it's the surface tension of the water that allows that bending to take place. Now what happens here is that the weight of water is defined by this pressure depth diagram right here. What this means, all of you have been to the bottom of a swimming pool. You've all felt pressure against your ears in the bottom of a swimming pool. That's all that means, is the deeper you dive, the higher the pressure. Now, what happens right here in this experiment is that rather than ordinarily, the water line should be right across here like this. But what happens is the water being drawn by surface tension and capillary pressure up this tube, that's displaced air. And the air that gets displaced forms a pressure curve like this. So here's the displaced air. This is what the water pressure should be. So the difference between the air pressure at this, or let me say the difference between air pressure and water pressure right here is measured as the capillary pressure, which is this difference right in here like this. So this is a scientific concept that I know all of you have seen. And in fact, how is this important? All of you know, for example, that water will flow upwards against gravity in trees and in plants and whatnot. And the process is just the same. It's capillary pressure that allows that water to work against gravity. So what happens here largely is that in a gas well, then gas shale, such as the Marcellus, is a rock that is water wet. It's water wet because that rock is deposited on the seafloor. And what has to happen is that in order for a Marcellus gas well to produce gas, which is right here, has to get through the rock to the open well. And the way that gas gets through the rock is it pushes its way through the very tight spaces called pore throats. Basically, it's the opening that allows gas to flow, or for that matter, any fluid to flow through the rock right in here like this. All right, so let's look at what capillary pressure is. Remember in that glass tube, when the water rose in the glass tube, you can take that glass tube and look at that convex surface. We're going back here. So this convex surface right in here is this convex surface right here. Here's water, here's gas right in here. And you see the gas pushing against the water. There's the convex surface. These grains are water wet, which means basically the water is trying to climb to your left as the gas is trying to flow to your right. And it's the water climbing to your left that prevents gas from flowing through this space right in here. It's a very simple concept. The capillary pressure is a consequence of the grains of the rock being water wet. All right, now, the final concept I want to introduce you with, and then we'll go to questions and answers, is a concept called imbibition. Now, most of you as undergraduates, when you were freshmen, the president of the university warned you about going to bars in New York State. When I was growing up, the New York State age for drinking was 18. I think it's been up to 21 right now. Is that true? Okay. But when I was an undergraduate, I could go to a local bar in New York State and imbibe when I was 18. So imbibition and imbibing beer is somewhat the same. So imbibition means the rock is going to drink water. So imbibition is a fluid flow process in which the saturation of the wetting phase increases and the non-wetting phase decreases. All right, now what do we mean by wetting and non-wetting phase? I'm going back here. The wetting phase, these grains, again, I told you, were like your dirty fender of your car. They're covered with a surface film of water. So that's the wetting phase. The non-wetting phase is the gas. These two don't mix. And so imbibition means that water will seep into the rock, displacing gas. Well, that's good, because of course what you want to do is somehow or another let the gas come out of the rock. And so, in a sense then, in order to get the gas out of the rock, the gas has to be driven with a pressure. And so with this diagram right in here, I've indicated that as a result of a surface tension between the gas and the water, water here, gas here, the water pushes against the gas with a force represented by this vector harder than the gas can push against the water. So that pushes the gas back in the rock. However, if the gas has a high pressure, then there's another vector. I've indicated that by this large arrow right in here. This vector, all of you remember from high school physics that vectors can add together. Those two vectors, that vector and that vector, added together make a vector that's larger than this. And this is a force balance equation in which the force of the gas now is sufficient to push the water out of the way. So somehow or another, then we have to generate conditions in which that takes place. And what I want to do right here is point out that the production of gas then is accomplished by pumping water into the well under pressure. And we have a fairly complex curve right in here. I want you just to look at this red curve. This red curve is a pressure curve right in here. And in order to cause the rock to open, or fractures to open, water has to be pumped into the rock at fairly high pressure. This blue curve is the rate of water flow into the well. We're not going to pay attention to this. All we're really going to do is look at this curve right in here, and I want you to understand 2 points. One of which is gas pressure in the rock, in the Marcellus, for example, is about 3,200 psi. But in order to fracture that rock, you can see that the water pressure has to be 6,000 psi higher than the gas pressure. That's this difference right in here. So anytime water is pumped into the rock at a higher pressure than gas, you can conclude then that this favors water flowing into the rock, not gas flowing out of the rock. So then the condition is illustrated very nicely right here. If any of you have ever visited Teganic Falls State Park, Teganic Falls State Park has a gas shale. It's called a Geneseo gas shale. Hydraulic fracturing is a matter of pumping sand and water down these individual fractures to open them up so gas can flow out. The problem is that water is 6,000 psi higher pressure than gas back in the rock. So the gas is back here, water is pumped down each of these fractures right here. The water is at 6,000 psi higher than gas. So naturally, the water is going to be driven into the rock. And that zone of water being driven into the rock is called the Leadoff Zone, or the zone of natural imbibition. So what this really means is that this frac fluid that everyone is all concerned about, particularly flowing back out of the rock, is actually captured by the rock by this process called imbibition. And it is the induced imbibition that drives the water into the rock. The problem is that this water driven into the rock blocks gas flow outward. So what happens, and this is a diagram of this, if this is the fracture face right here, all of the space next to the fracture face is completely filled with water. That prevents gas from flowing out. So here's the gas right here that you want to have flow out into the well so you can produce it. The frac fluid is driven into the rock. What happens then? So what happens is that there is a period of non-production. Most gas wells are allowed to sit without production. We would say they're shut in. And they're shut in to allow a period of redistribution of the treatment water. These are the millions of gallons that you put down on the rock that don't come back out. And that redistribution of treatment water then is sucked, if you like, or driven further into the rock. Now remember what I said was imbibition is the tendency for water, the wetting fluid, to drive into a rock where the water saturation is lower. Water saturation is very low where you have gas. So water is naturally imbibed further into the rock, and this period during which a well is shut in is that period right here that allows natural imbibition to occur. The water flows into the rock further. And what that does is that allows gas to flow through the porosity of organic matter to the edge of the well. If you imagine the fracture in the rock is right here, there's an interconnected network of organic matter called kerogen that is gas wet that will flow to the well bore as this water is naturally imbibed in the rock. And so, just in conclusion, and what I've done is I've indicated that the geological processes that operate mean that without a shadow of a doubt, the 80% of the water that is put down in these gas wells is imbibed in the rock and sequestered forever. And any of the fuss that anyone might raise about water somehow getting out of this gas shale and into the groundwater table, that fuss is ill-founded. So, okay, what I do is I'd be glad to answer questions about this. I hit you with a little bit of social science and then a little bit of hard science in terms of talking about the Marcellus. Okay, there's going to be a bunch of questions, and I look forward to the questions, believe you me. Yeah, please.
Okay, so given that the USGS has continually decreased their estimates of reserves, and the SEC is investigating whether reserves were vastly overstated, and beyond that on a global scale, it's still really marginal. Can you explain why this is so important that will collapse into authoritarian dictatorship if we don't exercise?
All right, now let me try to repeat the question. The question, the premise of the question is somehow or another, the USGS is more of an authority on gas reserves than other people that have made estimates. Is that correct? Is that what you're assuming?
No, I just said everyone who's made estimates has been continually reducing their estimates. Even companies have been reducing their estimates.
So you think that everyone is reducing estimates. Okay, let's presume that is true. Then what is the next part of the question?
Then why is this so incredibly important that the end of the world would go to it?
Yeah, that's an easy question. It can be answered on a number of planes. One of which is, let me remind you that we've just spent the last 10 years fighting two resource wars, one in Iraq, one in Iran. And the reason the armies are over there, of course, is that we're trying to protect Middle Eastern hydrocarbons, PTUs, that help us in our lifestyle. And if there is any way that we can bring those troops home by producing domestic hydrocarbons, I view that as a good thing. Now, let me point out that in Pennsylvania right now, there have been, let's say a couple thousand well pads. With the combination of the deaths in Iraq and Iran, there have been 3 bodies brought home in body bags per well pad. Now, if you were to ask any one of those families, would you trade 1/3 of a well pad in the United States for the life of your son or your daughter? You know what the answer is going to be, right? This is the trade we've got to make. There is a risk in everything we do. That's one answer. The second answer, of course, is that when we pay for foreign hydrocarbons, basically what we're doing is we're draining our national treasury, sending that money overseas. And so these hydrocarbons domestically are a chance to spend that money on local economies rather than just plain shipping it overseas by the sackful. That's the second thing. The third thing that becomes very important is to consider the way that electricity is generated in New England. In the last 10 years, because of gas from the Marcellus, New England electrical generation has been able to shut down 2/3 of its coal-fired electrical generation capacity. And as a result, America, for the first time in terms of CO2 emission, is approaching the Kyoto Accords, which of course is a tremendously positive thing. You can't argue with that. I mean, can you? Right? So, again, if you want to continue to bring bodies home from overseas, if you want to continually drain the American economy, sure, yeah, we don't have to frack. I mean, you know, the other issue, of course, is the one I pointed out, which is there is a local responsibility. Geneva right now is using frack gas from other portions of the country. Don't you think that it's fair that New York State should somehow or another share that burden? There's a number of these reasons that all of them point to this particular resource as a wonderful thing that's happening. Yeah, go ahead. Next question.
All right. I think the big question we're all wondering is, does fracking help or hurt biodiversity?
Does fracking help or hurt biodiversity?
Yeah.
Actually, you know, the number of people that come up from Texas that carry Texas viruses, you know, head colds and whatnot, has, as far as I can tell, diversified the fauna of head cold viruses. So as far as I can tell, it's helping biodiversity. Next question.
I tried to follow along, so if you have to repeat yourself,
Yeah,
I'm sorry, but
be pleased to.
what prevents the fracking fluid from undergoing the same capillary pressure that the gas undergoes that brings it to the surface?
Fluid is of course water, and gas and water are immiscible fluids, so they don't mix together. And basically, when one goes in one direction, the non-wetting fluid would go in the other direction. And capillary forces are just incredibly strong, particularly in the size pore spaces that are involved. And again, let me remind you that it is the capillary forces that, for example, allow nature on the surface, at least to allow plants to continue living. If it weren't for capillary forces, we would not have plants. All right, so what happens largely is that these gas shales have such small pore spaces in them that they form a seal. It's called a capillary seal. That capillary seal has been present for the last 200 million years, long enough to keep gas that's 200 million years old in place. If this rock property can hold gas in place for 200 million years, water, which is far more viscous and far less able to travel through a rock. Remember that the rock flow, the rate of flow of any fluid through a porous medium is inversely proportional to viscosity. The higher viscosity, the slower the flow. And so if these seals on formations like the Marcellus are capable of keeping gas, a very low viscosity fluid in place for 200 million years, frac fluid doesn't stand a chance of getting out through this capillary seal.
Thank you.
Yeah, over here's the question.
So, when you...
That way everybody can hear that.
Go special. So, you know, I heard that there are a lot of dry wells that they tried fracking and then they couldn't get anything out of it. So there are a lot of, you know, wells that are left behind without any like supervision in Pennsylvania. Is that true?
I'm unaware of wells that are left behind, largely because it's illegal to do that.
Right.
And the state is regulated by a government agency called the Pennsylvania Department of Environmental Protection, which, if they caught companies doing that, first of all, would make them manage the wells properly, but then would probably even kick them out of the state. I mean, the Secretary of the Department of Environmental Protection said that he has the authority to kick companies out of the state. And you wouldn't want to have that happen, particularly if you had considerable investment already in the gas shales of Pennsylvania.
Well, we're known to give out exceptions, like Engelder. You know, that's a company that makes the frac juice that got exempted from Clean Water and Air Act by the Vice President of the United States, and just got one exception from them. So we're known to give out exceptions like that. So rules would be bad.
Let me point out that the company you're talking about is Halliburton, right?
Right.
And the exemption was an exemption that we would all agree probably didn't help the industry at all. It was an exemption in terms of revealing the chemicals. But if there is a chemical spill, then that particular case immediately comes under the Clean Water Act and is managed by that law, so that it does not, that thing called the Cheney loophole or the Halliburton loophole in no way exempts industry from good behavior. And the way the Clean Water Act and Clean Air Act are written is that immediately upon some sort of spill, the Clean Water Act and Clean Air Act have no authority whatever.
But that's after a spill, so the damage has already been done. So then we get to know what's in there. So we don't get to know what's in that chemicals that's going into our ground. And once a spill happens, then they'll tell us what's in there. So that just doesn't sound right, you know.
Well, that's not.
Sense.
It turns out that industry, as I've indicated, recognized that particular exemption was unfortunate. It did not help the industry. And right now, there is a collaboration of all of the companies on a website called Frack Focus to reveal exactly what's put into the water, exactly what's spilled. And so what you're doing is referring backwards to the way it was 5 years ago, not presently. And right now, the industry is bending over backwards, having recognized that it made a mistake with this Halliburton Cheney loophole, to be very transparent and very, very straightforward. Yeah, go ahead. This young woman, what's your name?
I'm Anna.
Anna, boy, Anna and I are going to talk all night long, I can tell. Yeah, go ahead.
Okay, so given that industry is currently sponsoring legislation to keep all of these exceptions in place, it doesn't seem like they're actually actively coming to the table. But beyond that, how?
Actually, let me ask you a question. What is the evidence the industry is currently sponsoring legislation to keep these
Well,
rules in
obviously
place?
they're not explicitly sponsoring it, but
So wait a minute, wait a minute. You made a statement, and now you're saying that your statement is not correct?
Okay, can I finish my statement? Okay, my statement was that senators in Congress and in the House and the Senate are sponsoring legislation, and that companies.
What senators? I mean, you've got to be specific in this debate. This is the whole point concerning scholarship.
Yeah, so every single year they propose legislation to overturn those exemptions, and every single year they're shut down. So that would be what I'm referring to. I don't know.
Is that true?
Yes. I can Google it.
Yeah, I wish that you would.
Alright.
All right, yeah, now we'll get back to you, Anna.
Okay.
Yeah, go ahead, question there.
I want to ask kind of a follow-up question about the whole issue, kind of risk with that. So, could you talk a little bit about, in your presentation, you kind of made the argument that looking at the automobile industry and traffic deaths, that risk is, you've been able to decrease risk for that. And kind of by implication that we might see risks declining in the future with regard to kind of fracking and oil and gas production. So could you give us kind of a quick overview of the regulatory history for Pennsylvania? What's happened there, what the experience is, and what you think best practices are like in terms of trying to regulate this industry?
Yeah, that's a very nice question, because in fact the industry has evolved along with the regulators. And the trick, of course, is that there's a symbiosis between industry and the regulators. Both of them are trying to achieve the same thing, which is minimize risk. And so for a long time there was a practice that involved releasing frac fluid into streams and rivers. The Pennsylvania DEP brought that to an abrupt halt a couple of years ago. There was, for a long time, the regulation that we've already discussed right now, that these chemicals would not be released in the public domain. The Secretary of DEP, and for that matter a number of other states, have required that the material data sheets be posted on the individual well pads, revealing all of the additives into frac fluid and whatnot. And this is something that has evolved over the last number of years. The regulations concerning the management of water have changed and evolved. More and more emphasis is being put on closed loop systems, which means that water that's frac fluid. Now, I'm not talking about fresh water. Fresh water is still stored in open ponds, but rather the frac fluid is stored in closed or in enclosed tanks. And that's something that has changed. Even the extent to which well pads are lined, for example, to mitigate spills if they should happen, has evolved with time. And the regulators, for example, deal with water withdrawals and are much more strict about where water can be taken out, and when water can be taken out. There are stricter regulations about how water can be injected into the ground in terms of disposal wells, so that the evolution of these things is ongoing and will continue going into the future. There's a question behind you right there. If you'd like to follow up also, go ahead.
Just one quick thing. So what about regulation of the things having to do with the integrity of the well casings? Are we making any progress on those kinds of things?
The integrity of the well casings is one of the trickiest that is facing industry. And the regulations right now are make sure it doesn't happen. And if it does happen, why then the individual company that has a well that's a problem is liable. And the consequence of that liability can be one of two things. One of which is the well casing can be re-cemented. That's called a squeeze job. The other is the well can just be plugged and abandoned, and that's happened more than once. The famous area around Dimick, where gas leaked from groundwater, leaked from shallow formations into groundwater, was one that was mitigated largely because 3 of the wells in the immediate vicinity of some of the more egregious casing jobs were just plain plugged and abandoned. Yeah, the question behind you there.
I'm not sure exactly what was on the mind of the student that was asking about the abandoned wells, but we had just heard recently that Pennsylvania has approximately 200,000 abandoned oil wells, only 4% of which have known locations. So he may have been alluding to that. We haven't even touched on the cases of re-injecting the fracking fluid into old wells, some of which may be associated with some earthquake activity in locations which don't have a history of earthquake events is admittedly wood chips are less energy dense than the fossil fuels, but they're only releasing the carbons that they've sequestered in their own lifetime, which is on the order of decades, not hundreds of thousands of years, tens of thousands of years on fossil fuels. And nuclear energy is off the charts in multiple ways. 3 Mile Island, Indian Point barely goes a month without problems, and Chernobyl is covered in sarcophagus after ever increasing larger sarcophagus because they had problems that cannot be contained to this day.
Was there a question, or was that just a statement?
Oh, I had a lot of questions all along the way, but there were so many things, so many points in your presentation that I wanted to have addressed, and those are some of them.
All right, if I can, let's go to the wood chips, for example. You're aware that one of the worst parts of burning coal, of course, is the carbon black that's emitted into the atmosphere, the smoke, if you like. And can you imagine what the Vestal Valley, which is the area around Binghamton, would look like if everyone burned wood stoves in the wintertime? I mean, you wouldn't even be able to drive down the roads as a result of that. And can you imagine what would happen with that kind of smoke with anyone that has any sort of asthma and whatnot? So there are a bunch of externalities that are associated with wood chips that really sort of take it right off the table in terms of its effect on the quality of the local life that goes beyond the issue of whether or not it's burning its own sequestered CO2. In fact, that's not the issue, it's these other things. Nuclear industry is a case where the industry has evolved with a safety record over time, and the nuclear reactor accident in Chernobyl is first of all well understood, and the Russians made lousy nuclear reactors. I would argue that we're much better at that right now than we ever were. The problem with the problem with U.S. reactors in the past was that they were all custom-made jobs, and it's recognized that if you go to mass-produced reactors where you have interchangeable parts and basically they're modular, the safety record of these things is going to be incredible compared with what's happened in the past. So I would say that when thinking about nuclear power, the issue still remains what to do with the spent fuel rods. And in that regard, what you'll find, I think, is that they will be used to make plutonium, which then can be reused in terms of power as well. There's a tremendous opportunity here that should not be taken off the table. You had a third point, though, that you wanted me to respond to. What was that? There was wood chips in nuclear industry and...
We had heard recently on our local radio station that there are 200,000...
Oh yeah, the abandoned wells. The abandoned wells are a reality. Remember that Pennsylvania started drilling in 1859, and it wasn't until about 1930 that state regulations started getting on to companies and made them responsible for closing these wells. Then along came something called the Second World War, and the Second World War really had an effect that was very delirious on the industry, which is that there was a steel shortage. And so the country, in search for extra steel to make tanks to put down the Third Reich in Germany, went around pulling up all the casing from a lot of the wells that had been abandoned. And the reality is, though, that most of these wells don't get anywhere near as deep as the gas shale, so that they will not be an issue. The gas shale, drilling down to the depth of the gas shale only started after about 1930, when the Oriskany was a formation that was tapped for natural gas in New York and Pennsylvania as well. most of those wells are known, but there is a risk, and there's no one that can guarantee that industry will be able to avoid these unknown wells. I mean, it just is, it's a risk every bit as much as large as windmills systematically killing all the birds that fly up the migratory pathways and whatnot. We've got to make some choices, and those choices in general are not going to make everyone happy. None of the choices are going to make everyone happy. That's not possible. Okay, question.
Is the Marcellus Shale Is the Marcellus Shale around Hobart College? Is it of high enough quality? Does it have enough organic carbon to be able to support fracking at prices anywhere on most what we ever have? I've heard that most of the high quality shale is in Pennsylvania.
Well, let me tell you, the Marcellus Shale around Hobart is wonderful shale, very high quality. The problem is that you really have to have a barrier or a zone of safety between groundwater and these gas shales. And I think there's general agreement that everyone in that, in the industry would suggest that a zone of 4,000 feet or something like that is sort of a minimum. And so you've got to go down to Binghamton before you actually have that zone of safety. The Marcellus Shale in this area, although it's very rich, wonderful gas shale, is too shallow and never will be an issue.
In that case, what about the Utica Shale? I don't hear too many people talking about it.
Yeah, the Utica Shale, I think in this region is also too shallow to be serviceable. I'm not sure about that, but I think that you've got to go further south in the state, even for the Utica Shale. The Utica Shale, there's also a risk that it may be over mature. So the Utica Shale is going to be more productive further west. Yeah, a question over there. Yeah.
Okay. So you've explained how when you...
Hey, Anna, don't go away.
I have to go. I have to go to class.
Did you find the answer to the question?
I did. It was sponsored by a Democrat from Ohio. And
It-
it's sponsored every year for the last
What-
5 years.
What is the name of the bill?
The Act to Repeal the Energy Act of 2005. And it's died in committee every year for the last 5 years.
Okay, good. Yeah, go ahead.
Yeah, so you've explained that when you put the fracking fluid down in these wells, it pushes with all the geology and science, the gas comes out. Well, some of these, and you mentioned the disposal wells for some of the frack fluid that does come up, the 20% or so. And I was wondering, because I know that EOG Resources in Chesapeake and some of these other companies are looking into those types of disposal methods. If you could explain the geology behind keeping the frack fluid down in those wells, because wouldn't something have to come back up if you're disposing it?
Okay, now what I described was the interaction of fluid with gas shale. So that has nothing to do with disposal.
Okay.
Disposal, on the other hand, requires a very porous, permeable rock, a great sandstone, for example. And the process by which disposal fluid is sequestered has very little to do with the internal wettability of the rock itself, aside from the fact that these would be water-wet rocks, these sandstones where a frac fluid is disposed of. But what the disposal wells would have to do is have sufficient depth so that there are seals on top. Seals meaning shales on top. These shales would have to be well below the both the Marcellus and the Utica. Those are pretty deep wells. These wells around Youngstown, Ohio, were just that. But they have, disposal wells have a much different property to them than the gas shale. And so whatever I was doing in terms of trying to describe the geology of this, I was not describing the geology that would make a disposal well work. Yeah.
I think at this point we've had you on the spot for an hour and a half now, Terry. So I think maybe we should kind of call it into things and thank Professor Engelder for coming and.